In this video, we are going to talk about Gram-Schmidt Orthogonalization, or GSO for short. It is a very important algorithm that forms the backbone of many interesting processes used throughout mathematics. The first important concept to understand to get a feel about Gram-Schmidt process is orthonormal basis. Let's take an example. Suppose I take R2, suppose this is the origin and these are my two axes. I give you two vectors like this. In that case, you know that they form a basis of entire R2. So if I give you any two bases, for example, suppose I give you 3, 1 and this one is possibly 2, 5, then since they are not along the same line, they are linearly independent and the dimension of the space is 2, and I have already given you two linearly independent vectors, so they constitute a basis. As a result, if I give you any other vector in this space, you can write them uniquely as a linear combination of these two vectors. That's any arbitrary basis. Now, when we work, most of the times we prefer to work with a very special basis, namely these two vectors 1, 0 and 0, 1. These actually define the two axes, x-axis and y-axis. This one gives you the measurement of the length along x-axis, and this one gives you measurement of length along y-axis. So these two red vectors also constitute a basis, but they have some distinct advantage over these black bases. This advantage is what makes orthonormal basis very helpful. So the definition of an orthonormal basis is it's a basis, but at the same time the angle between the basis vectors are 90 degrees and they are also of unit norm or unit length. It is not important that these two things must be aligned with the axis. You could very well have something which is like this and something which is like this. That is also perfectly okay. For example, I might have one of them as 1 by root 2, 1 by root 2, and the other one is 1 over root 2 minus 1 over root 2. They will constitute an orthonormal basis of R2. Here is the general definition. Call a set U1 to UD of vectors an orthonormal basis, abbreviated to ONB, of some subspace V of Rn. This less than or equal to sign means V is a subspace of some Rn if these three conditions hold. Number one, it has to be a basis. So every vector can be expressed uniquely as a linear combination of these UIs. Then each of them must be of length 1. And if you take any two vectors in this list, not the same thing twice, I not equal to j, then their dot product will be equal to 0. That is, their length is 1 and they are mutually perpendicular. In case you drop this condition, that also has a name. In that case, you will call it an orthogonal basis. Orthogonal basis. If you have this, you have an orthonormal basis. Let us quickly remember the definition of dot product, which is also called inner product, though inner product is somewhat more general than dot product being the most important special case of this. But in our lecture, dot product and inner product will mean the same thing, and they're defined like this. I have two vectors in Rn. In that case, their dot product is defined as you multiply them component-wise and add. That is the definition of dot product. Now, I like to write my vectors as column vectors. That is, I want to write them as n by 1, not as 1 by n. In that case, you can express this as matrix multiplication x transpose y. Understand this? X transpose is a horizontal vector, row vector, and this is a vertical vector. So when I multiply it using the usual matrix multiplication rule, I have this times this plus this times this, etc., up to all the way like this. So this is a way of expressing inner product or dot product using matrix multiplication. The next concept that you have to remember in order to understand Gram-Schmidt orthogonalization is that O and B's are good things. We take an example to illustrate the point. Suppose I start with R2 and I have got two vectors constituting the basis of R2, and I want to express this red vector as a linear combination of these two vectors. Then I am trying to express my red vector minus 2, 3 as a linear combination of 1, 2 and 3, 1. I know from the very definition of basis that this is possible and uniquely true. I should be able to find scalars A1 and A2 such that this holds. How do I find it out? The only way that seems to be available is just writing it out as a system of equation. There are two equations in two unknowns. A1 into 1 plus 3A2 equal to minus 2. A1 plus 3A2 equal to minus 2. Similarly, this equation. So solving two equations in two unknowns is the only way that will enable you to find the coefficients in general. However, if I start with an orthonormal basis, O and B of same R2, and now I want to express minus 2, 3 as a linear combination of these two vectors, I have a simpler way out. I first give names to these vectors. I call this O and B U1, U2 and this new vector V. In that case, I am looking for A1 and A2 that satisfies this equation. Now, instead of solving two equations in two unknowns, I shall do something which is available only for orthonormal basis. Namely, I shall take dot product of both sides with U1. Let's see what happens. U1 dot V equals A1 U1 dot U1 plus A2 U1 dot U2. Observe that A1 and A2 being scalars, they quickly come out of the dot product. However, now you see U1 dot U2, that is just 0 because U1 and U2 are mutually perpendicular. And you know U1 dot U1, that is nothing but the norm square of U1, summation of all the component squares. So that is equal to 1. So this is simply A1. Thus, I have directly a closed form solution for A1, and that is A1 is equal to U1 dot V. I wanted to find the contribution of U1 in V, and it is very easy. Take V dot product with U1, and similarly A2 you can do U2 dot product with V. Because of this thing, O and B's are a lot easier to work with. So once you have an O and B of a given space, you can express any vector in that space very quickly in terms of linear combination of the O and B. That is something which you cannot do for an arbitrary basis. That's why I said O and B's are good. This brings us to the important question that if I give you any subspace V of Rn, some Rn, you know that a basis always exists. That's a theorem that you can prove that for every vector space there is a basis, and if it also happens to be a subspace of some Rn, then there is a finite basis. You can prove it in a very constructive way. Suppose V1 to Vk is a basis. I know it always exists. Is it true that any such subspace also has a O and B? Is that true? Because we see that O and B is good, but do these good things always exist? Well, the answer is yes, they always exist. And not only that, there is a very routine algorithm by which you can take any basis. You just take any basis and feed it into that black box, and out comes an orthonormal basis. So it's like a filter that converts any basis into some orthonormal basis. A very useful algorithm, and it is this algorithm which is called the Gram-Schmidt orthogonalization. So remember, it's an algorithm which takes basis of any arbitrary subspace of some Rn, and in a routine way churns out an orthonormal basis of the same subspace. Now we are going to understand how the Gram-Schmidt orthogonalization process works. It will help if we consider an analogy first. Suppose we have got three sets, V1, V2, V3 with some overlaps, etc. Now we want to cover the same ground as V1, V2, V3, that is, we want to have the same union. However, we do not want these overlaps. In other words, we are interested in getting three other sets whose union will be same as this union, but they will not have any intersection. Now here is one simple way of constructing them. What you do is you start with V1 and leave it intact. That is my V1. The new sets I will call U1, U2, etc. So I take U1 just equal to V1. Okay, now I plan to take U2 equal to V2, but I can't do that because if I take U2 equal to V2, then there will be this overlap which I want to avoid. So I take only that part of V2 which is not already taken care of by V1. So I take my U2 in this way. I take U2 like this, so it is V2 minus U2. So this minus here means set minus. I wanted to say this minus U1. U1 is same as V1. So the thing that is already taken care of, I leave it out. So you see V1 and V2, their union is same as union of U1 and U2, but they are also disjoint. Okay, now I come to U3. I define my U3 as V3, but there's a problem because if I take it to be entire V3, part of it is already taken care of by U1, part of it is taken care of by U2. I will remove those parts from V3 and the remaining thing I shall call U3, which means from this I am removing the part of V3 which is already inside U1, that is this part. Also I am removing the part which is inside U2, which is this part. So I get rid of these and I define U2, U1, U2, U3 with the property that they have the same union as my original things. However, they also have the additional property of being disjoint. Now let's understand how this is similar to the problem that we are trying to tackle. We shall start with a particular basis. V1, V2, V3, there will be vectors. We want to get a new set of three vectors U1, U2, U3 such that their span will remain the same. In this case, their union was remaining the same. But in the original basis, V1 and V2 may not be perpendicular, so their dot product could be non-zero. Here, their intersection could be non-empty. But in the output, U1, U2, U3, if you take any two, their dot product should be zero. The analogy here is their intersection is zero. And the way we proceeded is exactly what we do in Gram-Schmidt process. We take the first one unaltered, then we take the second one, subtract from it whatever is already taken care of the first one, then take the third one, we remove whatever is taken care of by the first two, and we can go on and on and on like that. Let's illustrate Gram-Schmidt orthogonalization process using R2. I start with these two vectors. They constitute a basis of R2. I want to convert them into an orthonormal basis. So I do exactly what I did for the sets. I start with U1, which I take just same as V1. Just this thing. Now I want to take U2 to be same as V2. Unfortunately, I cannot do that because this angle does not appear to be 90 degrees. So what I do is I remove from it the part of V2 which is already taken care of by U1. What is meant by that? By this we mean that I split it up into two components. There's one component which is perpendicular to V1 and one component which is along V1. So if I take this then I can split it up into two parts. So consider this rectangle of force. It's a parallelogram of force where this is perpendicular. This component is component of V2 along V1, and this is the component of V orthogonal to V1. And V2 is made out of this plus this. Now this thing we really do not need to keep in the basis because it is already along the direction of U1, which we have taken care of. Instead, we shall take only this component. So we shall take V2 minus component of V2 along U1. So understand this very carefully. So my final output will be, the first vector is U1, that is same as this. The second vector will be this, that is my U2. Now obviously you can see that they are still a basis, and by the very construction they are mutually perpendicular. Now you might object that what is the guarantee that their lengths will be 1? Indeed, their length need not be 1 the way I have done it. So I have only got an orthogonal basis, not an orthonormal basis, but that is very easily remedied. All that you have to do is you have to divide this by its corresponding norm. You take the unit vector along it. Similarly, here also you divide it by its norm. So you immediately get an orthonormal basis. This is exactly the procedure that we are going to follow in general Gram-Schmidt orthogonalization. Here is the general Gram-Schmidt orthogonalization process. I start with this input V1 to Vk, a basis of whatever subspace you are working with. Then Gram-Schmidt orthogonalization will process it to produce an orthonormal basis U1 to Uk. And it processes in the following way. It will take just the first vector here as your output first vector. Of course, it will take the unit vector along it, that is, it will divide this vector by its norm. Then the next one, U2 will be just V2 minus the component of V2 that is already taken care of by U1. Whatever you get, you take the unit vector along that. Then you come to U3, same idea, you take V3 minus, you subtract whatever is already taken care of by U1 and U2 that you have already constructed, and you go on like that. So U4 will be V4 after you take out the effect of U1, U2 and U3, and you go on like this. And you might be wondering whether I can always apply unit, because if accidentally something becomes a zero vector, there is no unit vector along zero vector because its norm is just 0. Well, that can never happen, because if that happens, this means they are not linearly independent. So it will not remain a basis. You can think more clearly about that and convince yourself that you will never run into any problem of any of these vectors becoming a zero vector. The way we describe the algorithm, we had to use one particular operation, namely finding component of one vector along another vector. Now how do we do that? Pictorially it is quite easy. Here is a vector V and you want to find component of V along U. This basically means you extend this line, you drop a perpendicular, and this vector is the component of V along U. But mathematically, how do you find it? It turns out that there is a very simple way of finding it. The formula is just this. You take U dot product with V divided by the norm square of U, and this is just a scalar because this is a constant, this is a number constant, it's just a scalar times U. That will give you this vector. Of course, any vector along this line must be a scalar multiple of U, but the particular scalar happens to be this. Now, how do you prove it? You can very easily feel it by considering just a two-dimensional analogy. If you consider this angle to be theta, naturally you understand it must be length of V times cos theta. And you can connect this theta with the dot product. So the dot product is actually has to do with the cosine of this angle, something that you have possibly learned in your HS days. But that is a good analogy. This result holds for any arbitrary dimension, because any arbitrary finite dimension at least. The main reason why it works is that you just consider any vector, any arbitrary vector along this line that will be of the form alpha u. You are looking for that particular alpha u such that this will be perpendicular. In other words, you are looking for v minus alpha u should be perpendicular to u. That is, you are looking for this dot u is equal to 0. That's your condition, right? This thing must be perpendicular to this. And you just expand it, you'll immediately get alpha must be equal to this quantity. That is a very useful thing, and once you have this, now you can directly work out Gram-Schmidt orthogonalization. Now this becomes even easier when you are working with u, which is unit vector, because there it will just become 1. So alpha is nothing but the dot product between the vector whose component you are taking and the direction along which you are taking the component. So it becomes even easier, and that is the thing that we need in Gram-Schmidt orthogonalization.